Greetings, class, and welcome to Chapter 2, The Chemical Basis of Life. In this particular chapter, we're going to look at a little bit of chemistry and how chemistry relates to our study of biology. And it'll kind of be a lead into Chapter 3, in which we'll talk about biochemistry and concentrate specifically on the different chemicals and compounds that are so important for life. And you might ask, why are we studying chemistry in this particular course? This is a biology course. Well, we have to remember that when we're talking about biology and we're talking about life, we're talking about things that are made of stuff. And things that are made of things are made of matter, right? And matter is what the study of chemistry is about. And so much about what we talk of in biology will be tied to chemistry. For example, talking about water, for example, which is really so important for all life. As you know, there's so much chemistry involved in water and the water molecule itself. So having a little bit of an understanding of chemistry will really help with our understanding of biology. In this particular chapter, we're going to concentrate on three different things. In the first part of the chapter, which we'll talk about today, we're going to talk about elements, atoms, and compounds. In the second part of the unit, we'll talk about the different types of compounds, such as ionic, covalent, that kind of stuff. And then in the third part of the chapter, we're going to talk primarily about water. Water will be the star of that part of the unit. So let's start at the beginning. As I mentioned a few seconds ago, when we're talking about life and we're talking about living things, we're saying that these things are made of stuff. And if they're made of stuff, that means they're composed of matter. And remember, matter is made up of atoms. And atoms, of course, are what make up elements, right? Elements and atoms are basically synonymous with each other. And there are about 25 different elements that are really essential for human life and other living things, but you really can break it down to four. The four really most important elements for all living things include carbon, oxygen, hydrogen, and nitrogen. These four elements make up about 96% of most living things, and these elements and different types of combinations with other things make up so many of the important compounds for life. For example, just staring at it right here, I can see carbon, oxygen, and hydrogen. The building blocks of carbohydrates, for example. So many of the compounds that we'll look at in the next chapter are going to be variations of these particular elements in compound form. And so what is a compound? A compound is a substance consisting of two or more different elements that are in a fixed ratio. For example, H2O is a compound. H2O is also, H2O2 is also a compound, but they're two different compounds. H2O is water, H2O2 is hydrogen peroxide. So even though they have the same elements, they're in different ratios, so they have different properties and they're different substances. They're both pure substances, each is different. Remember from your middle school physical science days, a compound is different than a mixture. A compound are substances, the elements of which are chemically combined, and they take on new properties unique to the combination of those particular elements. Whereas a mixture, remember, is where you have combinations of things, but each one of those substances or particles, whatever they are, still retain their individual properties. Here's another example. You have sodium, which is a metal, a very reactive metal. You have chlorine gas, which is a very dangerous gas. You combine them together chemically, and when they're together as sodium chloride, they have different properties than the individual components that make them up, and it's something now that we need for life. Isn't that interesting? And here's like a little cross-section of a human. You can see here those four elements that we mentioned, making up so much of a human. But there's also all these elements as well, which are very important as well. Some elements are, on that slide there, if you noticed, are also present in very, very small amounts. We call those trace elements. And even though they're available in very, very small amounts, they're still very significant. One example would be fluoride, which we get in our toothpaste. It's also added to our drinking water. That helps reduce tooth decay. Iron is another mineral like that. We take in trace amounts necessary for our blood to capture oxygen. Iodine, another one we find in our iodized salt. That's important for healthy thyroid function, and that's just to name a few. So even though they're in trace or small amounts, they're still very important. Now, as we said a few moments ago, the building blocks of matter are atoms. Atoms are the smallest unit of matter that still have all the properties of that particular element. So, for example, one atom of helium will have the same exact properties as a balloon full of helium. There are 3 particular subatomic particles that we want to be familiar with in this particular class, and of course you'll learn more if you take chemistry and physics later, and those include neutrons and protons, which are found in the nucleus of the atom, and those 2 components together make up basically the mass of the atom, which is in that dense central core, and then the electrons, which orbit the nucleus in the electron cloud. These elements are organized together on a table we call the periodic table of the elements, and that particular table is organized in terms of atomic number, increasing atomic number. The atomic number is the property that describes the number of protons for a particular element. The proton number is what differentiates one element from another. Here's the periodic table. Remember, on the outside we have what are called the representative elements. These are the elements that follow the rules of the periodic law of the best, and then in the middle we have the transition elements, which are their rules are a little bit trickier. And then attached on the bottom here, for convenience, we have the rare earth elements, the lanthanides and actinides. The modern periodic table is arranged in order from increasing atomic number, starting with number 1 here, and then it goes across, and then down left to right. The horizontal columns are called families. And then, the vertical columns, I think I said horizontal. The vertical columns are called families or groups, and then the horizontal rows are called periods or rows. So again, I think I mixed that up a little bit there. The vertical columns are called families or groups, and those particular elements within a particular family or group have very similar properties. The elements within the horizontal rows or periods can be very different as you move from left to right. A couple of the properties we want to talk about include the atom's mass number. The mass number is the sum of the number of protons and neutrons in the nucleus, and that's generally a whole number, and it's just the sum of those 2. So if I needed to find something like the number of protons or the number of neutrons, I could subtract, if I knew one or the other, I could subtract that from the mass number, and it would give me that missing value. Protons and neutrons do not have to be the same. The atomic mass, this is a little slightly different. The atomic mass, which you'll find on your periodic table, is generally a decimal number because it represents the average of all the different forms of that particular element. Because some atoms have multiple forms, and we call those isotopes. Isotopes are a form of an element that have the same number of protons, but they have a different number of neutrons, which gives them a slightly different mass. So for example, a nitrogen atom has 7 protons, and its most common isotope has 7 neutrons. So its mass number would be 14, and we would call that nitrogen 14. And then there's an isotope version of nitrogen that has 9 neutrons. So 9 plus 7 is 16, so we would call that nitrogen 16. This is a typical Bohr model of the atom. Sometimes referred to it as the planetary model, in which you have the nucleus in the middle, almost like the sun. And you have your protons and neutrons that you find there. And remember, the protons you get from the atomic number, and the neutrons you get from subtracting the mass by the number of protons. And then the electrons is the same as the atomic number. So in this case, we have 2 protons, 2 neutrons, 2 electrons. This is an atom of helium with its mass number 4, atomic number 2. For the correct electron configurations for each energy level, and this is an energy level, or sometimes they call it an orbital shell. For the correct configurations for those electrons in each one of those energy levels, how much is in each energy level, please refer to the periodic table I posted on Canvas. But do remember, the element's number of energy levels also is the same as the row number that the element is found in. So in this particular case for helium, if we go back to our periodic table, we'll see helium happens to be in row 1. Okay, so it has 1 energy level. Additionally, for the elements, if you look at the group number on the top, the group number will tell you the number of valence electrons. And the valence electrons are the number of electrons in the outermost shell. So if we go back again for a second, like all these elements here in group 1, lithium, sodium, potassium, all these elements, regardless of how I draw the atom and the number of electrons they have, the very last energy level for all these will be 1 valence electron. Group 2, all these elements, beryllium, magnesium, calcium, all those elements there, will have two valence electrons, and it's those valence electrons that are crucial for the interactions between the elements to form compounds. Now here's some examples of isotopes of carbon. We have carbon-12, which has a mass number of 12, carbon-13, a mass number of 13, and carbon-14, which has a mass number of 14. So you can see the number of neutrons changes the mass. It also gives it slightly different properties, which allows scientists to then take advantage of those properties to do for different things. For example, we do like to use radioactive isotopes in many aspects of science and industry. We can use radioactive isotopes as tracers to study the movement of materials, say, for example, inside living things. We can use that kind of radioactive imaging to capture images, say, for example, of brain tissue. We could also use radioactive isotopes in the treatments for things like cancers and stuff. So again, it shows you how science and technology support each other. Our understanding of science leads to better technology. And here's an example for us to close out our lesson. You can see some imaging instruments here, and you can see the brains of a healthy person versus an Alzheimer's patient, courtesy of our understanding of radioactive isotopes. And so that's where we'll stop for today, and then in our next section of notes, we'll talk about the different types of chemical bonds.